Okay, we have like 3 slides to finish material that would be on the test, and then I'm going to go over a few questions on the test and review for the final exam. So we had this slide in the class yesterday during lab. The decibel is defined as 10 times log of intensity over intensity 0. Now, something that I find interesting, you may have like your sound system at home, the sound system I have connected to my TV, for instance. It gives the sound in decibels. And depending on the source, I actually listen at minus 20 to minus 30 decibels. Now, I'll give you a hot tip. There is no way that I'm listening at minus 20 decibels based on that equation if I0 is the threshold of hearing. Because if it's minus 20, oh, by the way, this was for Alex's. Alex set up a coupled oscillator. You have a spring and you have a pendulum. So you set it in motion and you have a very complicated motion because you have 2 oscillators working together with different frequencies. Okay, so that's why I left that up, just so you could see the kind of stuff that Alex is going to have to solve in classes next year. So back to this. A negative means that you have the thing on top is smaller than the thing on bottom inside the log, which would mean that your intensity is less than the thresholds for hearing and you can't hear anything. So that can't be what it is. Does anybody else have a stereo system like this, or at least know what I'm talking about? Okay, one person has one and one person nods his head. What this means for my stereo is that I'm listening at 20 decibels less than the recorded level. So it's recorded with a certain level, how loud it's going to be. And I have my amplifier set for 20 decibels less than that, because how loud they have it recorded for would work better in a big room, not in my little TV room. And so this calculation here is done using intensity 0 is the intensity it's recorded at. And so I might wonder, how is the intensity I'm playing compared to the intensity it's recorded at? Are you wondering as well? Are you bereft of curiosity this late in the game? People are nodding their heads, yes. Physics is all about this curiosity. So if I want to solve this for the ratio of intensities, I would just take beta over 10 is equal to the log of intensity over intensity recorded at. And then, as we did yesterday, 10 raised to the beta over 10 is 10 raised to that thing, or 10 to the minus 2 is equal to intensity over intensity up. So if I'm listening at minus 20 decibels, that means I have the intensity 1/100th of the level it was recorded at, which seems crazy until you remember that we have such a large range, dynamic range that we can hear. I record church services at church, and we have some people that have a high dynamic range when they're talking. And so it might go up to, once again, we're doing the maximum level before it starts giving static down. And so we try to keep it like minus 12 decibels below where we're going to have saturation and get damage to our sound quality. And some people will go from like minus 14 up to minus 4. Minus 14 to minus 4, that's a factor of 10 times the intensity change, which is pretty extreme. The main culprit for that has moved on, so it's not as much of a problem. Okay, our one and only clicker question for the day, and give me a second because okay, it's open now. This is the last clicker question of the semester. The sound intensity 0.250 meters from a roaring lion is 0.250 watts per meter squared. What's the sound intensity level in decibels? Notice all of the numbers end with 4. That's because 4 is the one significant digit that you get when you do the log of 0.25. Well, it's the log. 4 is the log base 10 of 25 if you want it. Arlene, Christian, Noah, Brittany, Peter. Okay, everyone's answered. So we have 15 that said the top one, 114, 5 that said 104, 0, 1, 1, 0, 0, 0. Okay, can anybody tell us a quick way to answer this without using a calculator? No volunteers? Okay, let's look at this because this is just, making you a more efficient you when it comes to math. So the first thing we're going to do is beta is equal to 10 log of the intensity, 0.250 watts per meter squared, divided by a reference intensity, 1.00, times 10 to the minus 12 watts per meter squared. The first thing to do in this, to get the answer without using your calculator, is to do that division. 0.25 divided by 10 to the minus 12. That means I'm going to add 12, so it'd be equal to, that is add 12 to the exponent. And the units cancel. The units have to cancel. So that's doing the division. Now comes the fun part. Rewrite this number as normal scientific notation. And then use the fact that logs, you can take log of A times B is equal to log of A plus log of B. And you simply separate it into 10 log of 2.50 plus 10 log of 10 to the 11th. By the definition of a log, that's a log base 10, what is the value for 10 log of 10 to the 11th?
11.
Okay, it's 10 times 11. He's got the idea right, just forgot there's a 10 out front. Log base 10 of 10 to the 11 is saying, what power would I have to raise 10 to get 10 to the 11? If you understand what that means, you know immediately that was 11. So this goes to 110. So I have 110 plus whatever 10 log of 2.5 is. Well, 10 log of 2.5 must be 4 because every answer had 4 there. Oh, yeah, you're right. That was supposed to have been 24. You're right. And so you quickly could say, well, it's got to start with 110, so that had to be the right answer. Now, most people didn't do that because at your level in life, most people simply rely on the calculator. But it is useful to think things through and use your understanding. Especially, let's say you become a physician, you have to do something like calculate a drug. You want to be able to do it accurately, quickly in your head. Now, what happens if you add 2 sound waves? A question I love to do is, one trombone plays with the intensity of X decibels. Or not intensity level. of X decibels. Intensity is watts per meter squared. Intensity level is decibels. If I have 76 identical trombones playing, what is the intensity level? I love it because, of course, that harkens back to the Music Man. If you have two sources that are incoherent, what that means is they're making their sounds independent of each other. There's not a phase relationship with the sound. Then you just add the intensities. So this problem is similar to that, except for we have this problem. Here's the problem. A metal lathe produces 90 decibel sound if you're a distance of 1 meter away. What if you had two metal lathes operating 1 meter away from you? Then how loud would it be? The intensity level, how would you do it? Does anybody have a quick way of doing this? Because there's a quick way. There's also a long way. I am just going to assume that everybody is really enraptured by this, and that's why you're sitting there going. So we have the intensity level for 1 is 90.0 decibels, and that's equal to, by definition, 10 log of intensity of 1 over the reference intensity. So the intensity for two of them because they're not in phase with each other, that is, they have no phase relationship, so they're incoherent, the intensity is just doubled, and using the same rule that I just used previously, that's equal to 10 log of 2 plus 10 log of intensity 1 over intensity 0. Well, we do all know that 10 log of intensity 1 over intensity 0 is what we started with. So that was my 90.0 decibels. And having a second identical one is going to increase the decibel level by, and you put this in your calculator, and you find 10 log of 2 is, okay, I'm going to point to James. Do you have it memorized? No. Okay, go ahead and calculate then.
3.01.
So it's 3 decibels louder. That's a general rule of thumb you use when you're doing sound processing. It's doubling the intensity if you go up by 3 decibels. Hence why I thought you might have that one memorized. Now you know. Okay, that's the end of material that could be covered on the exam. There is no additional homework. The last homework assignment is due tonight. There's a supplemental homework, actually. I shifted them back. One that shows for today, one that shows for Friday. But the last homework is due tonight. And step through working with the intensity levels is what could be on the exam. So now I'm going to review for the exam. But before I go to reviewing for the exam, I want to look at the most troubling problems from the exam that we just took. So just some information here about the exam. The 3 problems that people scored the worst on by far were problems 15, 11, and 5. And so I'm going to go over those. The problems with 15 and 11, the 2 worst problems, were both people not paying attention to the units. It wasn't that they didn't understand the physics. If they were in the 16 through 20, they would have had much higher scores. But people didn't pay attention to the units and thus got the problems wrong. The scaling that I used, here's the actual scaling. I took the raw score plus 5 divided by 0.9541. 0.9541 was the highest score after adding 5 and not counting extra credit. 2 people got over 100% because of doing this. A second way of looking at it is the raw score times 1.0481 plus 5.24. So everybody's score got boosted by 5.24% plus then the scaling part. So let's look at those problems that had the biggest difficulties. And like I said, 2 of them was just units, and that's going to apply for any test we take. So going at these in the order they arrived at the 3 bad ones, if an engine were constructed to perform under ideal conditions, for example, there would be no losses due to friction, what would be its efficiency? Most popular answer? That was the most popular. But it's not correct. The second law of thermodynamics is the law that says that you cannot convert all of your energy from heat into mechanical energy. There's always going to be some wasted heat, some heat exhausted. That's why our heat engines always have a QH going in, a work going out, and a QC going out. So it's always going to be less than 100%, but of course greater than 0%. And what kind of engine will give us the best possible efficiency? Yeah. The Carnot engine will give us the best possible Okay, so it's not friction and other non-ideal things that are removing energy that keeps us from having 100% efficiency. It is the fundamental laws of thermodynamics. Okay, number 11. Suppose a gas-filled incandescent light bulb is manufactured, blah, 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 blah. Neglecting any change in volume due to thermal expansion or gas leaks, what is the pressure if you're at pressure 1 equals, not 20, 1 atmosphere at temperature 1 equals 20.0 degrees Celsius. Pressure 2 equals what at temperature 2 equals 60.0 degrees C. And we notice that it says gauge pressure. So these pressures I wrote are absolute pressures. They're the total pressure. What is the equation you use to solve this? The ideal gas law. One person pulled out the Van der Waals gas law. So we're going to have PV equals nRT. They did not give us the volume. They did not give us the number of moles. Some people could have, nobody did, at least that I recall, say, well, you can't solve it because you have too many unknowns. What we do is we just say, well, P2, V2, N2, T2, divided by P1, V1, N1, RT1. And then we take the fact that tells us no change in volume, which means that my volumes are going to cancel. And it doesn't leak, so my ends don't change. And of course, R is a constant, it changes. And I'm going to have P2 is equal to P1 times T2 over T1. At this point, there are two pitfalls that different people made. The first pitfall is saying this is equal to 1.000 atmospheres times 60.0 degrees Celsius over 20.0 degrees Celsius, which gave them 3.00, well, you only have two sig figs, so atmospheres. What's wrong with what I just did? The what? I didn't convert to kelvins. This is not a change in temperature. If it's not a change in temperature, you must use kelvins. So what I needed was 6 degrees C plus 273.15 over 20 plus 273.15. And that gives me 1.136. Of course, I only have 3 significant digits, so it'd be 1.14 atmospheres. And so a lot of people answered 3 atmospheres. A lot of people answered 1.14 atmospheres, but that's not correct either. What's the remaining problem? Gauge pressure. It said gauge pressure. And so pressure to gauge is equal to pressure 2 minus 1 atmosphere. I just put 1 for infinite significant digits. Is equal to 0.136 atmospheres. Now, if we go through and because we do have 4 significant digits because in the Kelvin temperature we had 4 sig figs. And so this actually is 4 sig figs before you do the subtraction. After doing the subtraction, it's 3. So this is the correct answer, 2 correct sig figs. So the problems there were units times 2 because you had to make sure you did it in kelvins and you had to make sure you did gauge pressure. Right? And the goal is not to trick students. I just copied these from the supplemental homework. Okay, now the one that we had the lowest score on of all the problems. Calculate the cold reservoir temperature of a steam engine that uses hot steam at 450 degrees Celsius and has a Carnot efficiency of 0.500. Well, we start with efficiency is equal to the work out over the heat added. And so does it give me the workout? No. Give me the heat added? No. But it also is asking for the Carnot efficiency. So, well, it's relating to Carnot efficiency. Carnot efficiency, using the Carnot engine, for the Carnot engine, we have a rule that the heat is proportional to the temperature. Now I can take my fundamental relationship for any cycle that work is equal to QH minus QC and say the efficiency is equal to QH minus QC over QH is equal to 1 minus QC over QH is equal to, using this relationship, 1 minus temperature cold over temperature hot. So now I'm looking for temperature cold and I'm given temperature hot. So solving this for temperature cold, I will switch the positions of the E and the ratio. So I have temperature cold over temperature hot equals 1 minus E. So temperature cold is equal to temperature hot times 1 minus E. And a lot of people got to this correctly. What do I put in for temperature hot? What do you think the majority of people did? They put in 450 degrees Celsius times 1 minus 0.5, and they got 225 degrees Celsius. That's not right. It's not a change in temperature. It's the temperature. When it's the temperature, you have to use kelvins. So what I needed here is to convert to kelvins. And so when I do that, it's 300 something. Let's see. That's 723 divided by 2 is 366. 361. 361 kelvins. And so then 361 kelvins minus 273.15 gives me my Celsius temperature, which it turns out is 88.4. And so that was the correct answer there. Both of these two I just did were ones that I trust most people understood. Looking at the work, it looked like they knew what they were doing, but they didn't pay attention to units. And that really is a vital thing that we started with at the beginning of the semester. The last one I wanted to look at here was the steam power plant, because a lot of people forgot that you don't have just two energy transfers. So the steam power plant operates between 550 C and 25 C. It exhausts 300 kilojoules of heat, so that's my Q cold because it's the exhausted. For every 480 kilojoules of heat that enters, so that's my Q hot because it enters. So my picture for the steam engine should have the Q hot, the Q cold, and the workout. So that's what the figure should look like. And then just like we did with number 15, the energy is equal to Q hot minus Q cold over Q hot, or the efficiency. And so the efficiency should be 480 kilojoules minus 300 kilojoules all over 480 kilojoules. And that is 0.38. So that's the actual efficiency. And then you had to do the Carnot efficiency, which we convert this to temperature. So we put 1 minus temperature cold over temperature hot. I just used that from what we did number 15 is equal to 1 minus 25 plus 273.15 over 540 plus 273.15. And that's the one that gave us 0.63. So in theory, with these temperatures, you could reach 63% efficiency. In actuality, we only have 38% efficiency, a little bit more than 50% of the theoretical maximum efficiency. Hence, not all that efficient. These numbers actually are realistic, by the way. Any questions about these problems? Then let's go to the reviewing. So starting in chapter 1, scientific notation. At this point, scientific notation should be really old hat. We've used it a lot. But make sure you're comfortable with it because there may be, keep in mind, everything's a maybe. I'm not promising any specific questions on the test. There may be questions on scientific notation. Maybe questions about significant figures. By the way, did I mention why I'm wearing a t-shirt today?
No.
I was so happy trying to get to work today, I forgot to put my shirt on. I got to work and took my jacket off. I'm like, hey, bro. Okay. Make sure you know the SI base units. Of everything we've done this semester, the base units were for mass, what was the base unit? Kilograms. For time, the base unit was? For distance, the base unit was? Meters. And finally, temperature, the base unit is? Kelvins. Okay, so those are our base units, the only ones we've used all semester. Everything else is a derived unit. So a Newton, we often think of a Newton as very fundamental, but it's a derived unit, has units of mass times acceleration, so kilograms times meters per second squared, joules for energy, kilograms times meters squared per second squared, and so on. So make sure you understand what derived units are, what base units are, and that you can analyze units. The prefixes, that's prefixes like, what does the prefix F stand for? No, the prefix. It does stand for frequency as a variable, but the prefix is femto, which is 10 to the minus 15.
We stopped at 12.
You stopped at 12?
Yeah.
Really? You should have from femto up to, I think, peta that you have memorized. Femto will be important next semester. We'll be talking about atomic physics where we use femtometers, also known as Fermis, named after Fermi, Enrico Fermi. Dimensional analysis is making sure you can look at an equation and determine what the units are of the answer. And graphing, yay. Make sure you understand how a graph of motion relates to the actual motion. And we've moved forward, so now we could talk about a graph of an oscillator and how that relates to the oscillator. So make sure you've remembered those things. Chapter 2, we had our kinematics. So our kinematic variables, position, displacement. One scalar has no direction. One is a vector, it has direction. Speed and velocity, same thing. Acceleration time. I assume everyone has these pretty well down. But if you don't, make sure you understand those. Kinematic equations and how to solve problems. So this was the first place where we really sat down and said, okay, when you're going to solve a problem, draw a figure that's illustrating what's going on. It's going to help you solve the problem, help you see what's happening. So in different situations, the figure that's going to be beneficial may be different. So for instance, for that heat engine problem, I wanted to see the schematic that shows the heat in, the heat out, and the work out, because those are the things that are going to help you solve the problem. So you draw the figure, identify what you know, identify what you're looking for, and then say, okay, so how do these work together? What equation is going to work for me? If it's a kinematics problem, you only have, 3 or 4 equations depending on how you count it. And we have one that has no time. If you don't have time, you're not looking for time, that's probably the one you're going to utilize. One that has no acceleration and so on. So you look at the equations and find the one that's appropriate, then you solve it, and finally make sure that your answer is actually a sensical answer. It makes sense. Things like a person jumps off the diving board and hits the water 2 meters below, how long are they in the air? If you have a negative answer, it's probably wrong. Right? It doesn't make sense to be in the air a negative amount of time. Then we went from one-dimensional kinematics to two-dimensional kinematics. What's different about two-dimensional versus one-dimensional? Independence of motion. We can take two perpendicular directions and treat them as completely independent. Motion in one direction does not affect the motion in the other direction. So when we talk about something like a projectile motion problem, I have a mass and I throw this mass, which I wouldn't do because we damage whatever it hits. We say, okay, let's look at the vertical aspects. What was its initial vertical velocity? Just the vertical components. You have to be able to break a vector into its components. And then given that vertical initial velocity, the acceleration, the vertical direction we know is always going to be on Earth, 9.80 meters per second squared down. We find down as the direction. And for this class, we say 9.80, even though, yes, it does vary based on location by a small amount. So we have that downward acceleration. We take the initial velocity and elevation, the final elevation, and we can figure out how long it's going to be in the air. Once we find out how long it's going to be in the air, then we turn to the horizontal direction, say, what was the initial horizontal velocity? Acceleration in the horizontal direction, what is the acceleration always going to be in the horizontal direction if you don't have wind blowing or something? 0. And so you can have that initial velocity and the time and calculate how far it's going to travel horizontally. That's the way you do trajectory problems. There's a lot of different ways of asking them, but they're all going to boil down to something of that nature. You need to make sure that you can show how vectors add tip to tail, explain the process, do it, that you can analytically break vectors into components and add the components, and then recombine them using the Pythagorean theorem and tangent. And of course, those pesky unit vectors. How do you label a regular vector? What do you do with the vector to make it so you know it's a vector? You have an arrow above it. Now in the textbook, it'll use bold often. or in textbooks, they'll use bold. But that's how you label a vector. A unit vector has the little caret above it. That means it has a magnitude of 1, and it's only really indicating direction. That's what a unit vector is. So we use those to keep track of directions. So make sure that you can interpret those. Chapter 4 and 5, dynamics. Dynamics is talking about why things move. Kinematics was talking about how they move. Dynamics, why they move. Newton's second law is our fundamental thing for dynamics. Things move because there's a force acting on. So net force is mass times acceleration. Remember, it's net force. Gravity is acting on me right now, but I'm not accelerating because of gravity. So if you put force is equal to ma, you're absolutely wrong. But net force is ma because the net force on me is 0, hence my acceleration is 0. We have the other two laws. First law is the law of inertia. Says things have a natural motion of staying at constant velocity. That's the first law. So the only way you break that constant velocity, that natural motion, is if there is a net force acting on it. Remember, Aristotle said there's a natural motion that's at rest. And so things would naturally go to rest. But Newton's law says, no, it'll stay at constant velocity unless something makes it change. And then the third law, for every action, there's equal opposite reaction. If object A applies a force on object B applies an equal opposite force on object A. So make sure you have those three laws in your head. They're very important. Free body diagrams are made so you can apply Newton's second law. So a free body diagram takes the object you're interested in and shows all of the forces acting on that object. Not forces the object is putting on other things, but the forces acting on the object. So if I look at my body, force of gravity is acting on my body down. Force normal from the floor is acting up. Those are the only two forces acting on my body, unless we get all technical, say, well, there's a buoyant force. You are displacing a fluid, air, and the air pressure is ever so slightly bigger at your feet than it is at your head. We would not consider the buoyant force in air, generally speaking. If you're in water, yeah, we consider it because the pressure changed a lot more going from head to toe. So make sure you can draw a free body diagram, understand the concepts, and understand why we do it so we can apply Newton's second law. Common forces, got them listed here. You should be able to use each one of these. This was where we introduced the springs that we used again this week when we were talking about motion or simple harmonic motion. So a lot of questions you had this week reuse stuff we learned a long time ago involving springs. That is, the force is minus kx. And in chapter 6 or 7, we learned that the potential energy for a spring was 1/2 kx squared. So those were both used heavily in this last week. We did not talk about stress and strain. I meant to cross those out and didn't. So those you don't have to worry about. Chapter 6, uniform circular motion and gravitation. You notice here I crossed off the satellite motion. Not going to have anything on satellite motion or Kepler's laws. But circular motion, you should understand what our rotational variables are and why it's useful to treat rigid objects using circular or angular variables. And then we have the kinematic equations, just like we had with linear, except for you replace x with angle, v with angular velocity, and the tangential acceleration with the angular acceleration. That's tangential acceleration to angular acceleration. What about centripetal acceleration? What's the difference in tangential acceleration and centripetal acceleration? Okay, centripetal is the acceleration toward the center necessary to keep something going in a circular path. So you have to have a force or a sum of forces toward the center to give you that centripetal acceleration. And we call that the centripetal force. Centripetal force is not a unique force. It is just the sum of the forces toward the center. Hence, on a free body diagram, you never show centripetal force because it's not its own force. If I were to take this and swing it around a circle, it would be the force of tension supplying the centripetal force. If it was a horizontal circle. If it's a vertical circle, it's going to be a combination of the force of tension and the force of gravity parallel to the string. So it gets more complicated with that vertical circle because of gravity being part of it. Tangential acceleration is the acceleration parallel to the motion. So tangential acceleration will speed it up or slow it down. The angular or the centripetal acceleration will change the direction. Universal law of gravitation is the force of gravity is really capital G, mass 1, mass 2 over the separation of the centers of mass squared. That's actually only true for point masses, but to a reasonable approximation, we take everything as a point mass. So I say, yes, I am a single point. And I calculate the force between me and anyone, say near a point. What direction is the force of gravity? It's always attractive. Next semester, we're going to start right off by learning about electricity. And we have electric charge. It comes in two varieties, positive and negative charge. Well, we have gravitational charge too. We call it mass. But mass only comes with one variety. It's monopolar. It's always positive mass. So the force of gravity is always attractive, whereas with electric charge, we have the two different types of charges, positive and negative, and we'll have both attractive and repulsive forces when we get to electric charge. And likewise for magnetism, we have two poles, as we call it, north and south. And if you get into deeper stuff, you'll learn that we have for the color force, we have the color charges that are red, green, and blue. How do we have red, green, and blue? Well, there are three primary colors of light, red, green, and blue, and there are three charges for the quarks, and so they chose to name them after the primary colors. That's for next semester. Chapter 7, work and energy. Energy is the ability to do work. You can have energy through two things. Through motion, we call that kinetic energy, or through configuration or position, we call that potential energy. Work is a force acting on something resulting in motion. So if I have a rock that I'm trying to hold up, but no, it comes down, then I'm doing a negative work on it because my force is up and its motion is down. If I push it up, then I'm doing a positive work because my force is the same direction as it's moving. And if I take that rock and I walk sideways at a constant speed, I'm doing no work, even though it's moving, because my force is perpendicular to the direction of motion. So make sure you understand those keys to what work is. Now with energy, with kinetic energy, we broke it up into two pieces. Translational, that is traveling in a straight line, 1/2 mv squared. And rotational, going in a circle, 1/2 I omega squared. New symbol I. What is I? The moment of inertia. Now, some people say the inertia, and that's wrong. If you say the inertia, that's meaning mass. The moment of inertia is the rotational equivalent to inertia. It's telling us about how easy or hard it's going to be to make something start rotating. Mass is telling us about how easy or hard it's going to be to make something start translating. So that rotational inertia, unlike mass, varies with positioning. So we had things like the skater with the arms out, the moment of inertia is larger, with the arms in, it's smaller. They have an angular momentum. Momentum was mass times velocity. Angular momentum, rotation equivalent to mass, moment of inertia, times rotational equivalent to velocity, angular velocity omega. And so if they're spinning, and they pull their hands in, their moment of inertia is getting smaller, but the angular momentum stays the same, so they have to spin faster. And of course, we have the problem with the motorcycle rider, one test to go, where the motorcycle rider leans to his right, the angular momentum of the tires pointing to his left, he leans to his right, which makes a torque about the tires that's forward. Newton's second law for rotation says that the net torque is equal to change in angular momentum over change in time. And so the change in angular momentum had to be the same direction as the torque. Hence, the angular momentum had to go from to his left to moving forward, making the front tire rotate and making him turn right. Right, those are complicated interactions, but interactions that you see all the time. If you ride a bicycle, you use it all the time. You don't think about it, but it's there. The chemical or the potential energies here, only the top two are ones that we have right now. The ones below, electromagnetic, chemical, and nuclear, are things that we'll talk about next semester. And we've talked about internal energy, that is the kinetic energy of all the little molecules and their potential energies as well. Vibrational energy, yeah, right. Acoustic energy, that's sound, energy and sound. We didn't talk about it except to say that waves transport energy. And so that's what the acoustic energy is the energy transported by those waves. Seismic waves, waves that go through the earth, also transport energy. How do we know that? Because they knock down buildings. Can't knock down a building without energy. The work-energy relation was very important. It's where I started with defining energy, really. The net work is equal to the change in kinetic energy. Net work can be broken down into the work conservative plus the work non-conservative, change in kinetic energy. But work conservative, by definition, is minus the change in potential energy. So we can rewrite this equation as work non-conservative is equal to change in kinetic energy plus change in potential energy. And this form is usually what we use to solve work energy problems. We say, okay, is there any non-conservative work? That would be work done by something like a person or by friction. Those are the two primary things that would cause non-conservative work. And or some external motor or something. If it's zero, then of course that's zero, and you have change kinetic plus change potential is zero. If it's not zero, well, you calculate it and you go in. You calculate the initial kinetic energy, the final kinetic energy, the initial potential energy, the final potential energy, and then you solve. So work energy problems are actually pretty simple. Work and energy, those are not vectors, they're scalars. So if you can solve a problem either with Newton's second law or work energy, it's usually easier to do it with work energy methods. Okay, I'm out of time, so we will pick up on Friday with chapter 8.